Hi everyone. So welcome to this course on advances in LLMs, and this is the lecture on instruction tuning or instruction fine tuning. So far we have discussed pre-training, right, and also fine tuning techniques, right. Pre-training gives you a lot of ideas about the language in general, right. Also there are studies which show that pre-training actually gives you the idea of reasoning, right, relational reasoning and other reasoning tasks or objective and instruction fine tuning. But the problem with pre-trained models is that those models cannot follow your instructions, right. So let's say, because ultimately their objective was to predict the next word, autoregressive model, next word prediction. So let's say if you ask the question, right, where is your school located, right. um, let's say this is the prompt or the input. The model will start asking more questions. Where is your college located at, right, and so on and so forth, instead of giving the answer. So people realized again in 2020 after the GPT-3 paper. So GPT-3 paper came in 2020. First GPT paper came in 2018. GPT-2 came in 2019, and GPT-3 came in 2020. And what they realized is that these pre-trained models are so powerful. Now GPT-2 to GPT-3, if you look at the size, is 100 times, 175 billion. So what they realized is that noticed is that with the scaling of the model is able to essentially do in context learning, right. If you ask questions, the model would be able to respond to questions sometimes, right. If you give examples, the model is able to follow the examples and so on. But they also realized that model is not suitable to follow all the instructions properly. Okay. So therefore they thought that we need further fine tuning, right, which will teach the model how to follow instructions, how to follow human instructions. So we'll discuss about different techniques in this lecture. But before that, huge news, a very big news, is that GPT-5 came, and I told you at the beginning that I don't know how many new models will come during this course, right. As the time progresses, maybe new models will come in. GPT-5 came on August 7, and GPT-5 is OpenAI's latest model, which is, according to the CEO, is smarter reasoning models, true multimodal, advanced coding, and so on. As usual, they performed they checked the performance of GPT-5 across multiple benchmark, right, and benchmark results are quite amazing. So if you are interested, you can look at this blog. Okay, so and they call this next generation AI. So maybe, yeah, I'm not very sure about the efficiency of, or effectiveness of these models, because there are many posts on social media which says that GPT-5 is not able to simply subtract 9.8 minus 9.11, right. But anyways, this is all about hype, and we will just live up with this hype. Okay, so we are discussing pre-trained models, and let us understand the problems of pre-trained models. Okay, let's say if you ask Llama 3 8 billion, right, which is also a open source model, that write a poem that describes a sun getting dipped in chocolate. Okay, and you see the model will produce this kind of responses. That model used to produce this kind of responses 2 years back. It should be a haiku, it should be about a sun getting dipped in a chocolate, and these two sentences would get repeated multiple times, and this is not a poem at all. So you see that the model is not able to understand the prompt properly, the instruction properly. So we need further fine tuning to teach the model how to follow instructions. So after pre-training, we will talk about instruction fine tuning, which basically let the model follow natural language instructions, right. And then we will also see later that instruction fine tuning may also not be sufficient. We need more fine tuning, right. And for further fine tuning, we need human alignment. For example, let's say after instruction fine tuning, you have an instruction tune model, and you ask what is the best way to lose weight quickly, right? You may see that the model produces a response like this: reduce carb intake, increase fiber and protein content, and so on. Or the model can say that you should stop eating entirely for a few days, right? Both of these answers basically are okay in terms of question. I mean, at least if the model generates these answers, you can say that the model knows how to follow instruction. But among these two answers, this answer is harmful. Okay, so the model should not generate this kind of answer. The model should generate this kind of answer. So for that, we need another fine-tuning technique which we call RLHF, reinforcement learning from human feedback. We'll discuss different variations of RLHF, different alignment techniques later on. But in today's class, we'll just see how from this prompt we get this kind of answers, right? Okay, so why instruction fine-tuning is needed? So next word prediction is quite obvious. Model knows how to predict next words, but model doesn't know how to follow instructions, right? The second objective is that we sometimes want the model to basically follow certain style or certain meta information or meta instruction. What is a meta instruction? For example, write a poem which would look like something written by Rabindranath Tagore, for example, right? Or write a Shakespeare style novel, right? So here the objective is not only to produce a novel or a poem, but also the style should also be maintained, right? So this is called meta instruction. But the problem is that for instruction fine tuning, we do not have data, ready-made data. What we have either free flow text data, right? Or what we have task specific data set. Task specific data set means glue, super glue, right? Big bench, this kind of benchmark where different tasks are there and the corresponding outputs are given. But these task specific data sets are not exactly instructions, isn't it? So the point is, how do we basically curate data for instruction fine tuning? Okay, so let's assume that you have curated instruction fine tuning data sets where there are instructions and the corresponding answers. Okay, and during your training time, you know the instruction and the answer, right? You feed the instruction on the and the answer to the model, right? And what is the task of the model? The task would be to predict the answers, the tokens in the answer one by one, right? So where is IIT Delhi located at? This is your instruction. Your answer would be it is located at Hotchkiss, for example, right? So both these things will be your input, and you calculate the loss at the token corresponding to IIT Delhi and so on and so forth. Clear, right? So if you have encoder decoder model, then it is straightforward. Your input will be the instruction and your output will be the response, right? And then you measure the cross entropy log likelihood of at every token, and you take the sum of the log likelihood, right? Conditional log likelihood. But here the important point to note is that we are calculating the loss only at the decoder level, not at the encoder level, right? So this is the loss, instruction fine tuning loss that people use in general, right? And if it is a decoder model, your input and output will be fed together to the model, and you will start calculating loss from here. So this is your instruction, right? And you expect the model to generate this. So you calculate the loss here with respect to the first token, then loss here with respect to the second token, right? And so on and so forth. Clear? And then again conditional log likelihood. So this is the objective function that people generally follow for all instruction fine tuning task. But we realized, we meaning our lab, okay, so we thought that this objective may not be entirely correct, because one can also if you completely ignore the instruction, if you do not compute loss on top of the instructions, the model may not understand the instruction properly, right? So we also understood that loss at the decoder level, at the response token level, would be more important than the loss at the instruction level, but both the losses should be important. Both the losses should be considered together. So so if you do not calculate loss on top of instruction, right, this is kind of same as teaching a child how to answer without understanding the question, isn't it? So what we thought in one of our very recent papers, that let us think of an objective function which gives weightage to both instruction as well as output, right? So you see here, so nt is the number of tokens, okay, present in the input, and so p is the instruction, mod pi is the so I equals to 1 to n means, so you have nt number of data points, right? And within, so you take one I, right, and first p is the instruction and then rest r is the response. So you take the cross entropy, you measure the cross entropy of the instruction tokens and cross entropy of the response tokens, and this is the weight. This is basically weighted average, and this is the weight associated with this, right? And this is a normalizing factor, which essentially takes care of the fact that you know, if the size of, I mean, this basically balances the size, the length of the token, right? So what we said is that this lambda p and lambda r, which basically balance the importance of instruction tokens loss and the output tokens loss, these two things should be there. But in our paper we haven't discussed how to come up with or how to assign these values of lambda p and lambda r. But what we showed is that if you, and we basically showed experiments across different combinations of lambda p and lambda r, and it turned out that these are some of the observations, and these observations are interesting. So it turned out that if the weight of the weight of the instruction token should range between 0 to 0.6, and the weight of the response token should range between 0.6 to 1. I mean, this range will basically give you the best answer, right? We also showed across multiple sets of experiments, models, that if you zero down the loss on the prompt token or the instruction token, the result will be suboptimal, and this is true across all the models: encoder only, decoder only, encoder, decoder only, and different types of decoder only models. And we call this fine tuning as weighted instruction fine tuning technique, WIT. And we also show that you know, it consistently shows improvement in generalization over conventional instruction tuning model. But they are also I mean, this not only produces better answer, but also it is less sensitive to prompt variation, right? If you change the prompt here and there, we see in most cases that the model produces completely different answer. So we showed using, so in one of our previous papers, we came up with a metric to measure the prompt sensitivity, right, of a model. And we showed that if we do weighted instruction fine tuning, then the model will be less sensitive to prompt perturbation, right, and may give you a stronger baselines for your experiments. I'm not going to details of this paper, but this is something that just to note. If you are interested, this is our recent TACL paper. You can look at it. Okay, but the remaining lectures, we will assume that the conventional instruction fine tuning objective will be followed. Okay, not the weighted one. So here the biggest problem, or the major problem, is the dataset collection, because we really do not have enough data set, and manual curation of such data sets are impossible, right? So if you look at the GPT-3 model, which came in 2020, and ChatGPT came in 2022, in between people tried out this GPT model, and we basically we gave free instructions to OpenAI, right? So OpenAI basically took our instructions, our prompts, and they curated their own data sets. But at the same time, there are open source models, right, which showed how to come up with better data sets. So for example, the FLAN dataset is the first instruction fine-tuning dataset, very effective, publicly available, handcrafted dataset. And in the T5 paper, they showed that if you use, this model is called FLAN T5. If you use this instruction dataset, then it would help model improve the performance. And let's look at this FLAN dataset curation strategy. So let's say you have this NLE task, right? What is this NLI? Well, what is NLI task? NLI task is that you are given a premise and a hypothesis, and your task is to basically identify whether the whether this is an entailment or not an entailment. Okay. So Russian cosmonaut, etc., said set the record for the longest continuous amount of time spent in space, right, and so on. And then your hypothesis is Russians hold the record for the longest stay in space, right? So this entails this, right? So the label is yes, and this data set is already given in your task, right? Because this is an entailment task, NLI task. From this data set, how can we get a instruction fine-tuned data set? How can I get the instruction, right? So what they said is that they manually curated for every task. They manually curated instruction templates. For example, this is the first template. Based on the paragraph, can you conclude whether the hypothesis is correct or not, right? This is first template. Second template is read the following and determine if the hypothesis can be inferred from the premise, right? Third template is can we infer the following, the hypothesis and the option, right, and so on and so forth. So these templates are manually curated, and then what you do, you convert such data set to an instruction fine-tuned data set. And how do you do that? You can use an LLM to do that. So you give this to LLM and you ask the LLM to essentially follow the template and generate a question. Okay. So this is the FLAN dataset 2021. So the problem with the FLAN dataset was that it's a very simple data, right? Mostly they used NLI for the data curation. So then the next paper came, and this is called supernatural instructions dataset. In supernatural instructions, they hired NLP practitioners, and then what they said is that for every task definition, again we are given a set of tasks, let's say in glue or super glue. For every task definition, you come up with the positive examples and the negative examples. The data can also be curated from let's say the Git commit, comments and issues in GitHub and so on and so forth. So they actually employed NLP practitioners, and they converted the existing data into task specific instruction data sets, and they claimed that here the tasks or the instructions are more complicated than FLAN data, right? So these are some of the ways to curate human aware data set, right? But then a bunch of papers came which said that we do not need any human intervention as such. We use LLMs to generate instruction fine-tuning data, right? And we do not need any human intervention at any point in time. So these are synthetic instruction tuning data set. These are cheap and easy to obtain, but of course it is not as useful or not as quality, at least quality wise it is not as useful as human curated data. But at the same time, you can actually curate a lot of data sets, right? Silver label data. So these are the 4 papers or 4 techniques which turned out to be really effective. The first one is self-instruct, second one is evolve instruct, third one is Orca, and the fourth one is instruction back translation. And all these are synthetic instruction tuning dataset generation techniques. Okay, let's go through this one by one. First one is self-instruct. So for the self-instruct, what is my input? My input is the task-specific data. I hope you understood the difference between task-specific data and the instruction fine-tuning data, right? So there are 175 seed tasks, and the tasks are available in the, let's say, glue benchmark or super glue benchmark, big bench benchmark, and so on. And for every task, one instruction is given and one instance is given. Now these instruction and instance are manually curated, and this is very less effort. For every task you need one instruction, right, and one instance. Okay, this is the input, and what they do is that from every instruction, let's say you take a task T, you have an instruction I, right? Now from every instruction you curate n number of other instructions, right? I mentioned earlier that, let's say, for the NLI task you can think of multiple instruction templates, right? So these are like templates or instructions, right? So what they did and how they did it, I'll tell you later. So there are 2 sets. Okay, one set is the human curated instruction and the other set is synthetic instruction. Okay, so in the first stage, so when the process starts, there is no synthetic instruction present in the data set. So this set is null, whereas you have instructions, you have one instruction per task, which is part of this human curated instruction data, right? So what you do, you first sample 8 instances, and they took 8. You sample 8 instructions from this set. Okay, so initially only the human curated instructions will be sampled, right? So you sampled 8 instructions, and then you ask a GPT model, let's say GPT-3, a big model, to generate more instructions, right, from 8 to, let's say, 800, right? Now the instructions that the GPT model will generate, some of the instructions are, let's say, the kind of same instructions that were already there in your data set, right? So what you do here, you check the similarity between the existing instructions and the GPT generated instructions, and if the similarity is very high, you discard. If it is low, then you basically add this to the synthetic instruction set. Okay, so now you are basically populating this SI set. You have human instruction and synthetic instruction. Again, you do the same thing. You sample 8 instructions from the set and you repeat, right? Now what they said is that among these 175 tasks, some of the tasks are classification tasks and some of the tasks are generation tasks, right? For example, sentiment analysis is a classification task. So they said that we need different treatments for these 2 different tasks. Classification task, we need a different treatment. Non-classification task, we need a different treatment. By the way, so we have only generated instructions. What else we need to generate? Bolo? Huh? Instances, the answers, right? We only generate instructions, but we don't have so what is instruction? An instruction can be, find the sentiment of the following sentence. This is the instruction. What is the sentiment of the following sentence? This is another instruction, right? But we also need the input output pair, right? The sentence itself and the corresponding label. So we need another another iteration. So what they said is that let us just first classify or identify the classification task instructions and non-classification task instructions. Why? Because if it is a classification task instruction, then in order to generate instances or input output pair, I will write my in context prompts or in context examples in a different way. If it is a non-classification task, then I will write my in context examples in a different way. And these are all, so there is no fine tuning as such, all basically prompt based output. So if it's a classification task, then your if it's a classification task, then your instructions, right, or your prompts would be output first prompt. What is output first prompt? Find the sentiment of the, so your output first prompt, in your output first prompt, your output will be given first and the corresponding instance. For example, let's say this is my task description. Given the classification task definition and the class labels, generate an input that corresponds to each of the class labels. If the task doesn't require input, just generate the correct class label. And this is my task description. Classify the sentiment of the sentence into positive, negative, and mix. Okay, and you see the first input is the class itself. So you want to generate a mixed class sentence. So right, so in this line you are writing class label is mixed, and let us generate a sentence whose sentiment is mixed class. Now this is your sentence: I enjoy the flavor of restaurant, but the service is too slow. Then your class is positive, and then you ask the model to generate the sentence of positive sentiment, and this is your so this is called output first prompt. Why? Because you first write the output and you ask the model to generate the corresponding instance. As opposed to this, if it's a non-classification task, then it will be input first prompt, right? Where basically, let's say your task is which exercises are the best for reducing belly fat at home. So this is your task, and you ask the model to produce the output. So input first and the output. See the difference? Now tell me why we need output first in case of classification. So the number of classes is known to us. Why do we need output first? Yes, very nice. So if we ask the model to generate first n instances with positive class, next n instances with negative class, right? We always want the dataset to be balanced, right? So if you do output first prompting, then you will make sure that the dataset will always be balanced, because this is up to you to decide. Okay. By the way, these are very simple concepts, but they use a different fancy name for this. Okay, so now this is the overall pipeline. 175 tasks, seed task, 1 instruction per seed task, 1 instance per task. You have the task pool, right? You ask a model, you use a GPT-3 to generate instruction, right? With the same process, right? And then you classify whether the task is a classification task or non-classification task. If it's a classification task, then you do output first. If it's a non-classification task, then you do input first, right? And you basically, and then they also have a filtering stage where they remove some of the spurious instances which are not that useful. That's it. Self-instruct, and they showed that GPT-3. This is GPT-3. This is T0, T5. They showed that if you do instruction fine tuning on GPT-3, right, with the self-instruct data, you see a boost, right? And if you use their model, which is called instruct GPT, right, you can see further boost, right? They also showed that if you first fine tune GPT-3 supernatural data set I mentioned earlier, supernatural data, right? You do fine tuning on supernatural data, and then you further fine tune with self-instruct data, you get further boosting and so on. Evolve instruction is another paper where they showed that self-instruct produces very simple questions, right? Let us make it more complicated, because the more you generate complicated instructions, the model will learn complicated things, right? And they said that there are two ways to make the instruction complicated. One is called the in-depth evolution. So you are basically evolving the instruction. So one is in-depth evolution, and other is in-breadth evaluation. Evolution. So what is in-depth evolution? Very simple idea. You start with a simple prompt. Let's say add x plus y, add x and y, right? And then you ask the language model to keep on adding more constraints to the instruction. So you have a seed instruction, right? So you have a seed instruction, and you ask either big models to make the instruction more complicated by adding more constraints. This is called in-depth evolution, because you are basically producing more complicated in-depth complicated prompt. In breadth evaluation is very straightforward. This is basically saying that, given a seed instruction, you curate multiple instructions of similar types, so breadth will increase. Okay, and this when you generate multiple instructions, let these instructions be complicated. All these are done by GPTs, by the way, no human intervention. You humans will only write the prompt. So this is the prompt that they wrote. I want you act as a prompt creator. Your goal is to draw inspiration from the given prompt. So given prompt is your seed prompt. Okay, to create a brand new prompt, this new prompt should belong to the same domain, right, as the given prompt, and so on and so forth. This is the prompt that they wrote, and the model generated the instructions. Okay, the Orca style instruction generation data is very straightforward. So some of you know knowledge distillation. In knowledge distillation, what you do, for example, there was this allegation to DeepSeek that DeepSeek used GPT's data, right? Some of you have heard of this. So in knowledge distillation, in data knowledge distillation, what we do is that we generate data from big models, and you use those data to train a small model. Right? For example, let's say you have a small 8 billion model, so you know that GPT-4 is superior to this 8 billion model. So you essentially write prompts to GPT-4. GPT-4 will produce responses. Then you take this instruction and the response, and you fine tune a small model. That's an 8 billion model. This is pure knowledge distillation, right? Data-driven knowledge distillation. But in Orca paper, they showed that GPT, ends up producing just the answer. Okay, let us make it complicated. Okay, so what they did, they wrote system level instruction to GPT-4, and then they asked GPT-4 to write the chain of thoughts, the steps. Okay, instead of only producing the answer, you write the chain of thoughts. And this will be the data for your model. Instruction back translation. So as the name suggests, what do you think? Back translation model, instruction back translation. You have a lot of unlabeled data. You have a lot of human written templates, right? You take a model, an LLM model, you ask the model to essentially generate questions from the data. So these are unlabeled data sets, unlabeled texts, right? So you first teach this model to generate questions from the data, right? And that question and the data itself, that will be your instruction fine-tuning data. Okay, so here you basically need to train two different LLMs. These are like simple approaches, but it turned out to be really effective in terms of, because these, after all, these are synthetic dataset generation process, and you end up producing a lot of data, right? Part of the data might be noisy, but such datasets are very useful for training bigger models. Okay, so some of the data sets which are publicly available for instructional fine tuning include FLAN T5 data, 11 billion size token, alpaca data. This is also a good data set. So right, so so people fine-tuned llama 7 billion with alpaca data. Then you have wizard language model, wizard LM data, which was used to fine-tune llama 7b, and then of course the Orca style data generation, which was used to fine-tune a Mistral 7 billion model. Okay, all right. So if you look at the side effects of instruction fine-tuning, not only helps the model understand the human instruction, but they also showed in different papers, they also showed that you do not need a lot of data set for instruction fine-tuning. Even let's say you have a model, conventional model with no instruction fine-tuning, and you have a model with only 6% instruction fine-tuning, you see the jump from 54% to 70%. With 24% of instruction fine-tuning data, 70 to 73, and with 100% instruction fine-tuning data, you may not see much jump, right? So the paper concluded that instruction fine-tuning models are quick learners. Even a small instruction fine-tuning would always help. Okay, that's it about instruction fine-tuning. In the next class, we'll discuss RLHF. Thank you.